In HSSC Part 2 Physics, we will discuss 10 chapters including electrostatics, current electricity, electromagnetism, electromagnetic induction, alternating current, physics of solids, electronics, dawn of the modern physics, atomic spectra, and nuclear physics. Let's start chapter number 11, electrostatics. Electrostatics is combination of two words, electro and statics. Electro means charges and static means at rest. So from here we get the definition of electrostatics, the study of charges when they are at rest. So in this chapter we will study stationary charges. Charge is a basic property of matter which is responsible for all electric and magnetic interactions, which means that due to charges, particles attract or repel each other. There are some properties of charges such as electrons have negative charge and protons have positive charge. Force of interaction, the force due to which similar charges repel and opposite charges attract each other, is called force of interaction. Between similar charges, force of interaction will be repulsive, and between opposite charges, force of interaction will be attractive. SI unit of charge is Coulomb. Magnitude of charge is 1.6 exponent minus 19 coulombs. Charge is always represented by E. Charge is quantized. Quantization of charge means it will be always in the form of n times E. E is basic or smallest unit of charge, which is 1.6 exponent minus 19 coulombs. It cannot be further divided by any number, so we take n as integer. Here we can see two similar charge rods and they are repelling each other. And here two dissimilar charge rods are attracting each other. Charles Augustin Coulomb got engineering degree and then he was selected in army as lieutenant. He did many engineering projects in France and then he got interest in pure physics. So he started research on pure physics. He was working on torsion balance and then found the force of interaction between charges. From this observation and experiment, he formed a law in June 1785, which is now known as Coulomb's law. Coulomb's law gives the electric force between two-point charges. Let us consider two-point charges plus Q1 and plus Q2. Because they are similar charges, that's why they are repelling each other. And the distance between them is represented by R. This system is taken in vacuum. Here F21 represents the force on charge Q2 due to charge Q1 and F12 represents the force on charge Q1 due to charge Q2. Here two dissimilar charges plus Q1 and minus Q2 are attracting each other. Statement of Coulomb's law. The magnitude of the electrostatic force of attraction or repulsion between two charges is directly proportional to the product of magnitude of charges and inversely proportional to the square of the distance between them. F is directly proportional to Q1 into Q2. Greater the product of magnitude of charges, greater will be the force of interaction between them. Let's say it equation number 1. F is inversely proportional to R square. It means that when we increase the distance between charges, force of interaction is reduced. And when we reduce the distance between charges, force of interaction is increased. Let's say it equation number 2. By combining equation number 1 and equation number 2, we get equation number 3, which is F is equals to K Q1 Q2 divided by R square. Here R is the distance between the charges and K is Coulomb's constant. K is equals to 1 upon 4 pi epsilon naught. Epsilon naught is permittivity of free space. Permittivity of free space means how much electric lines of forces are allowed to pass through the space. Its value is 8.86 exponent minus 12 coulombs square per Newton meter square. By putting the value of permittivity of free space in this equation, we get the value of Coulomb's constant, K exponent 9 Newton meter square per Coulombs square. Coulomb's law application. Here we have taken two similar charge spheres. Because they are similar charge spheres, that's why the force of interaction between them is repulsive and they are repelling each other. We can observe that when this charge sphere comes closer to this charge sphere, the position of this charge sphere is changed from 4 centimeters to 5 centimeters. This is because when the separation between charge sphere is reduced, the force of repulsion is increased. Coulomb's law in vector form. Because force is a vector quantity, so we have to write it in vector form. Here we have taken two similar charges plus Q1 and plus Q2. Because they are similar charges, that's why they are repelling each other. We know that F21 is force on charge Q2 due to charge Q1 and F12 is force on charge Q1 due to charge Q2. And R is position vector, which is the distance between these two charges. And for defining the direction of vector, we need unit vector and we write it with cap. Here R cap 21 is unit vector pointing up to Q2 from Q1 and R cap 12 is unit vector pointing up to Q1 from Q2. So we can write F12 is equals to 1 upon 4 pi epsilon naught Q1 Q2 divided by R square into R cap 12. Let's say it equation number A. And similarly, we can write F21 is equals to 1 upon 4 pi epsilon naught Q1 Q2 divided by R square into R cap 21. Let's say it equation number B. As R cap 21 is opposite in direction to R cap 12, so we can write it R cap 21 is equals to minus R cap 12. Minus sign shows the opposite direction. Putting this value in equation number B, we get F21 is equals to minus 1 upon 4 pi epsilon naught Q1 Q2 divided by R square into R cap 12. Let's say equation number C. Since right sides of equation B and equation C are similar, so we get F12 is equals to minus F21. This equation shows that both forces are equal in magnitude but opposite in direction. We have already discussed Coulomb's law in vacuum and now we are going to discuss Coulomb's law in material media. For example, we have taken water and placed our system into it. Our system means we are not going to change the magnitude of charges and the distance between them. It is similar as it was in previous case in vacuum. So we can write force of interaction between these charges in this medium, which is F is equals to 1 upon 4 pi epsilon m q1 q2 divided by r square. Let's say it equation number D. Here epsilon m is permittivity of medium, which is equals to epsilon naught into epsilon r. Epsilon naught is permittivity of free space, which means that how much electric lines of forces are allowed to pass through the vacuum. And epsilon r is relative permittivity of free space, which means that how much electric lines of forces are allowed to pass through the medium. Epsilon r is also known as dielectric constant. By putting the value of epsilon m into equation number D, we get equation E, which is F medium is equals to 1 upon 4 pi epsilon naught into epsilon r into Q1 Q2 divided by r square. By separating epsilon r in this equation, we get F vacuum divided by epsilon r. Let's say it equation number F. This equation shows that force of interaction between charges in any medium is less than force of interaction between charges in vacuum for the same system. It is due to the relative permittivity of the medium. This factor reduces the force of interaction between the charges because it is divided by F. Here we have taken few materials and their relative permittivity is shown here. For vacuum, relative permittivity is 1. For air, it's 1.0006. For benzene, it's 2.284. Relative permittivity of germanium is 16. Relative permittivity of water is 78.5. For glass, it's 4.8 to 10. For mica, it's 3 to 7.5. For paraffin paper, it's 2. For rubber, it's 2.94. For ammonia liquid, it's 22 to 25. Relative permittivity of materials may change with change in temperature.